This is this is the last topic from asynchronous counter or ripple counter, that is a decade or BCD counter. Till now we have completed asynchronous up counter, asynchronous down counter, asynchronous up down counter, and mod 6 counter as example of not whole count modulus, that is a mod of 4, mod of 8. In up counter and down counter, up down counter, we have gone through the mod 4 counter, mod 8 counter, and I have given example in the last class, that is the mod 6 counter. By this way you can build up mod 7 counter, mod 9 counter, in any of the mod counter. So this decade counter or BCD ripple counter is a one kind of asynchronous counter, that is called mod 10 counter, basically mod 10 counter. So why this mod 10 counter is so important? Because it is a BCD counter. That's why it is very important for us. So for this is the last topic from the asynchronous counter, that is a mod 10 counter. So as we know that the modulus, the maximum count possible, count counting possible through this mod 10 counter is a 10 minus 1, that is 9. So we can count from 0 to 9 by this mod 10 counter or BCD decade counter or BCD ripple counter. So it can be a up counter, it can be a down counter, or it can be up down counter. But still now we can count 0 to 9. 9 is the maximum count. So if I convert this 0 and 9 to the binary, that means 0 can be written like this, 4 zeros, and 9 can be written like this, 1001. So as if I see this, if you see this here, 4 bits are there, 4 bits are responsible. So 4 bit, that means we need 4 flip flops for this purpose. To make this decade counter, we need 4 flip flops. So for flip flop, we can draw the state diagram so that it may be a clear more. So 0 0 0, then 0 0 0 1, 0 0 1 0, 0 0 1 1, 0 1 0 0, 0 0 1 0 1, 0 1 1 0, 0 1 1 1, 1 0 0 0, and 1 0 0 1. That is a state diagram of mod 10 counter. Mod 10 asynchronous counter. So here we, if we gone through the regular counter or regular asynchronous counter of 4 bit, so 4 bit counter can count up to 15. That is a mod 16 basically. 4 bit counter is a mod 16 counter. We are generally constructing the mod 16 counter by 4 bit. That is a 4 flip flops can construct this mod 16 counter. So we are escaping, or we are means we are reducing the steps, that is 10 11 12 13 14 15. So some of the steps we have removed from this counting sequence, and after 9 we have initialized the counting to the 0. So generally for by using 4 flip flop we can count 1 0 to 15. But in case 0 is same, but we are counting 0 to 9. So this is also same thing that we have applied, the same procedure that we have applied in the last mod 6 counter, designing mod 6 counter. So mod 6 counter also we have connected one separate combinational logic, combinational circuit, that is a NAND gate for modifying this mod 8 counter to the mod 6 counter. Now we are means converting mod 4 counter to the mod 3 counter, mod 4 counter to the mod 4 sorry mod 16 counter to the mod 10 counter by connecting one combinational logic. So before going to do this combination, derive the combination logic, we should write the truth table of this counter so that it should be easy for us. So for this decimal equivalent first, then 4 flip-flop are there. So 4 flip-flop means 4 output. So Q3, Q2, Q1 and Q0. And clear, that I have told you in the last mod 6 counter designing, that we need a clear or preset asynchronous inputs for controlling this or for direct the counter to terminate their counting sequence in a specific provided pre-provided state, that we need one asynchronous input. Asynchronous input, generally two asynchronous inputs are preset and clear. So here also we are using clear input to initialize the counter. So I am giving CR as a clear. Now I can write the combinations. Combination possible 0 0 0 0 0. So 16 8 zeros and 8 ones are 4 zeros are next 2 zeros, 2 ones. Next 0 1 0 1. Now we can write the decimal equivalent of this 0 1 2 3 4 5 6 7 8 9 10 11 12 13 14 and 15. So this one is a mod 16 counter, basically truth table of mod 16 counter. And now we can want to terminate this counting sequence after 9. After 9 we want to force the counter to be initialized. So by this can be possible in two ways also, as a previous one. So up to the 9, if we make the clear input 1, so clear input 1, that means the flip flop is working as a normal flip flop. So counter is working as a normal counter. It starts counting from 0 and up to 9 it is counting without any hesitation or without any prevention. So still now this 9 up to 9 it is 0, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yes, up to 9 it is 0, 1. After 9, that is on 10, if we make this clear input 0. And after 0, that means clear 0 means the counter is in initial condition. Counter is resetted. Counter is resetted means counter all counting outputs are now 0. Q0, Q1, Q3, Q3, all are zeros. That is initialized. Again, it starts counting from 1, 2, 3, 4 after that. So these steps are don't care. These 5 steps are don't care. Now from this we can derive, we can follow another path also. That simultaneously, if we track this Q3 and Q1, when Q3 and Q1 both are 1, So at that condition, we can make this clear to the 0. So if we check once that Q3 and Q1 simultaneously, when it both are 1, then at that condition Q1 and Q0 and Q2 is 0. It may be 1, it may be anything. But simultaneously, if we track this one, Q3 and Q1 is 1, at the stage at a stage when we receive the sequence Q3 and Q1 simultaneously 1, that time we can initiate we can change the clear to 1 to 0. This is also one method, and one method, another method, we can get this clear boolean expression of clear from the K-map. So here it is a 16 point. So 16 points are there. So you can do this 4 by 4. So MSB and LSB, MSB is a Q3 and Q2, LSB is a Q1 and Q0, Q1 and Q0. Now we can place this clear values of clear. So here it is 0, 1, 2, 1, 3, 2, 4, 5, 7, 6, 8, 9, 11, 10, 13, 14, 16, 15. No, 15 sequences are there. 12,
7 मिस हो गए थे.
12, 13, 15, 16 and 15, 12, 13, 15, 14. So you can place this as 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, then don't care, then 0, all are don't care. So now we can group this. So this one is a one group. We can make this one. And considering this don't care condition, we can make one another group. So from this, we can write the clear equals to this one is a Q3 complement plus this one is a Q1 complement. From the De Morgan's, we can write this Q1 and Q3 whole complement. So the same function that can write the NAND gate. That previous one also we have got that one NAND gate, that is here Q1 and Q3, and it is a clear. It is clear. So can draw the circuit of this gate counter. So I need 4 flip-flops for this. Q2 complement, Q3 complement, Q3 complement. Now I can connect the T0, T1, T2, T3 with a logical one. Can connect also preset and clear. And is a negative edge trigger. Can connect the preset also. Both clear and preset are the active low. MSB. Now we can connect the clear with the combinational logic. That is, I need one NAND gate for this, and I need to connect the Q1 with the Q3. So now we can verify the circuit, verify this circuit with the truth table. If I give if I give 0 0 0 0 0, all are zeros. If I get the for counting sequence 0 0 0 0, 4 zeros are there. So 4 zeros, that means at that time both Q1 and Q3 is 0. So this one clear is 1. Clear is 1. So clear 1 means is active low. So counter is acts as a normal counter. It increase your its counting sequence after increasing when Q1 is 1 and Q3 is 0. Q1 is 1, Q3 is 1 of the input is 0, NAND gate output is 1. So that clear is also off condition. So at that time when Q1 and Q3 simultaneously 1, that time we can say that the clear is 0. So when clear is 0, the counter is in reset condition. That counter is resetted or initialized. All the outputs Q0, Q1, Q3, Q2, Q3, all outputs are becomes 0. So that the initial condition comes. After initial condition, again it starts counting from 1, 2, 3, 4 at 9. After crossing the 9, again it's initialized by the clear input. So this counter is working like this. Is called the decade counter. Is counter is called the decade counter or BCD counter. Decade counter and or BCD counter. So this is almost completed. I have completed the asynchronous counter portion. So in this asynchronous counter, I have completed up counter, asynchronous up counter, 3-bit down counter. You can check in your home that by 3-bit 3-bit to the 4-bit, you can construct one 4-bit the same way. You should follow the same pattern or same procedure for 4-bit counter or 2-bit counter or 4-bit counter or 16-bit counter, say mod 16 counter or 2-bit counter also you can construct by your own. So I have given you idea about the 3-bit up counter, 3-bit down counter, 3-bit up down counter, mod 6 counter and mod 10 counter. So almost our asynchronous counter portion completed. Next I will start the synchronous counter section.